This is part 2 of aerobic energy production during exercise, fat metabolism. Your body stores its reserved energy supply largely in adipose tissue in the form of molecules called triglycerides. These are made up of 3 fatty acids connected to a backbone of glycerol. During exercise, hormones cause the triglycerides to separate, so the fatty acids can leave the fat cell, enter the bloodstream, and be delivered to the exercising muscles. The amount of fatty acid that then enters the muscle depends in part upon the concentration of fatty acids in the blood. So substances like caffeine that break down fatty acids and increase the fatty acid content in the blood would increase the energy supply to the muscle in the form of fat. That's why studies show that taking 3 to 6 grams per kilogram of caffeine before an endurance event can increase performance by 2 to 3%. Triglycerides are also found inside the muscle, which also get broken down into the fatty acids and glycerol. The glycerol only provides a small amount of energy, with the majority of the energy coming from the fatty acids. Whether the fatty acids come from the blood or inside the muscle, before we get energy out of them, they need to enter the mitochondria. This requires the breakdown of one ATP molecule and the presence of carnitine. As a supplement, L-carnitine doesn't appear to help with weight loss, but it may improve exercise performance, although the results of years of studies are very inconsistent. Once inside the mitochondria, the fatty acids undergo a series of reactions called beta oxidation. This chops up the fatty acid into smaller 2-carbon-long segments, starting at the second or beta carbon. The 2-carbon-long segments form an acetyl-CoA molecule, and in the process an NADH2 and FADH are also formed. Then the shortened fatty acid goes through beta oxidation again, producing another acetyl-CoA, NADH2, and FADH. This continues for the entire length of the fatty acid. For example, the fatty acid palmitic acid is 16 carbons long, so it would go through beta oxidation 8 times, producing 8 acetyl-CoA, 8 NADH2, and 8 FADH. The NADH2 and FADH carry their hydrogens to the electron transport chain, where they're used to make ATP, as I covered in aerobic energy production part 1 on carbohydrate. Meanwhile, the acetyl-CoAs enter the citric acid cycle, where they are broken down in the same manner as acetyl-CoA from pyruvate that came from the breakdown of glucose in glycolysis. In fact, during exercise, your muscles get energy simultaneously from both glucose and fatty acids. Even though fatty acid metabolism provides more acetyl-CoA and therefore the potential for more ATP than glucose metabolism, fatty acid metabolism is slower and less oxygen efficient than glucose metabolism. The amount of energy from either carbohydrate or fat that the muscles use during exercise depends upon the intensity and duration of the workout, as well as the diet and training status of the person. Speaking of intensity, you may have heard that you burn more fat at lower intensities. Well, even though the percentage of energy coming from fat compared to carbohydrate is greater at low intensities, you have to remember that the total number of calories being burned is pretty low. For example, during 60 minutes of low intensity exercise, about 66% of the energy is coming from fat. But the total amount of calories burned is about 180, which means you burn about 120 fat calories and 60 from carbohydrate. However, during 60 minutes of a moderate workout, only 33% of the calories come from fat. But the total number of calories burned was 540, meaning you burn 180 fat calories, more than you did at the lower intensity. But as the intensity of exercise gets near maximum, the percentage of energy from fat becomes nearly zero. The intensity level where you burn the greatest amount of fat calories is referred to as fat max, and it occurs on average around 65% of maximum, but it can range from 30 to 90%. One of the reasons you switch from fat to carbohydrate as the intensity increases is that higher intensities rely more on fast-twitch fibers, which are very anaerobic and burn mostly carbohydrate. The duration of exercise also influences fat metabolism. The longer the aerobic workout, the greater the percentage of energy comes from fat, while the percentage from carbohydrate decreases. So with only 2,000 calories of energy available from carbohydrate in the average person, and around 120,000 fat calories in a non-obese person, you think you could continue doing aerobic exercise indefinitely. However, the citric acid cycle requires intermediates, supplied by pyruvate from carbohydrate metabolism. So when carbohydrate levels like glycogen get low, the necessary intermediates aren't available for the citric acid cycle to keep up. This slows down the rate or speed of energy production from aerobic metabolism, despite having plenty of fat stored. This is why marathon runners fear hitting the wall around the 20-mile mark, because that's about when their glycogen levels start to run out. When that happens, their running speed drops, because now their primary fuel source comes from the slower fat metabolism. Carbohydrate loading the week before an endurance event can increase glycogen stores, and along with consuming carbohydrate during the event, can delay or prevent fatigue due to glycogen depletion. On the other hand, consuming a high-fat diet increases fat metabolism during exercise, which would preserve glycogen levels and in theory also improve performance in endurance events. The research isn't clear on which a high-carb or high-fat diet is best on improving endurance events, but the literature leans towards high carbs. Finally, compared to untrained people, endurance-trained people burn more fat during exercise, in part because training increases oxygen supply to the muscle, overcoming one of the limits of fat metabolism. So that's how your muscles use fat during exercise. Post your questions below and watch my other videos on aerobic metabolism from carbohydrate and how aerobic training improves energy production. Thanks for watching, and as always, my answers come from peer-reviewed research.